An important approach to doing our analysis and understanding the stability of our processes is the Laplace transformation. So the Laplace transformation is simply the multiplication of our original function f of t with the exponential function e to the minus st, where s is in general a complex number. And at the moment, we'll just treat that as a constant. So we'll think of s as some constant. And yes, it is a complex number, but it's still a constant complex number. And in the integration, we are integrating out time. So that's the way to think of definite integration, right? We integrate with respect to that variable. And in a sense, then we've added up everything under the curve with respect to that variable t. And so our function will no longer contain time. We've in effect integrated out over all possible values of time. And what's left is the area under that curve. And so the only remaining variable then is s here. And so we obtain the function f of s. So that's why we think of this as a transformation. We are transforming an original function in time into another function in s. So that's our Laplace transformation. And this is a linear transformation, which we won't show in this condensed version of the notes, but it enjoys all the privileges of linear transformations. And so looking at some examples, and of course, these examples are carefully picked because these are things we'll actually use later. But if we want to transform the exponential function, so let's say our time function f here, let's say that was e to the kt, because that's what we've been discussing now. We were interested in the stability and we were concerned about the k part having real parts that are positive. So the Laplace transformation of e to the kt, simply by applying this definition of the transformation, is that we multiply by e to the minus st with the original function, so e to the kt here, and we integrate out time by going over all possible values of time from 0 to infinity. And so if we are taking the product of two exponential functions, we can see there's a common t here. So we can group out that t, we can group out a minus t, leaving us with s minus k here. So that's our kernel. And then when we integrate this, of course, we are integrating in time. So s minus k is a constant. And so it's a constant times t. And so 1 over that constant that pops out in the integration, leaving us with the integration function e to the minus t times s minus k, which is here. And we are going from 0 to infinity, so 0 to infinity. And if we think about at infinity, we have e to the minus infinity. So e to the minus infinity is a 0. So it approaches 0. So we can say the upper limit is 0. And then e to the 0, right? When we say e to the minus t here, and then t is a 0, then we know this is going to give us a 1. So it's going to be minus, and then the minus here, in fact, there's a minus sign missing here. So let's add that in, because this integration, the constant is minus s minus k. So when we apply the 0 in here, we get a 1, and it's in the lower limit. So it's minus that lower limit. And so we are just left with 1 over s minus k. So we can see for an exponential, the constant, the time constant there appears in the transformation as an argument shift of the s. So that's the transformation of an exponential. Then a little more abstractly, if we do the Laplace transformation of a derivative, so in a sense, this is an operator on an operator. We can think of derivative or differentiation as an operation as well. So it's an operation on an operation. And so it's e to the minus st times the function itself, which is dy dt. And if we recall our integration of a product of two functions, if we position them this way, if the two functions are f and g, then the result will be f times the integral of g, minus the integral of the derivative of f times the integral of g. So this this outer integral applies to both these as products here. So we could more explicitly write it like so. So that's integration for a product. And in our case, if we let the f be the e to the minus st part, and we let g be the dy dt part, then we can see we'll have e to the minus st out here. And then we want to integrate g, and g is a derivative. So the result of that will, of course, be y itself, right? So if we integrate dy dt with respect to t, then we'll get the function y itself. So that's the first part here, right? So that takes care of this piece. And then in here, we want the derivative of f. So the derivative of f here is going to be minus s times e to the minus st. So we can see the s here, and then the minus multiplied with this minus gives us a plus. And then e to the minus st we have to retain. It is a time function, so we keep that inside the integral. And then again, it's the integral of g, and as we've just said, integral of g is y itself. So that's what we have now. And if we look at this first part, we can see e to the minus infinity. Again, that's a 0, so we can ignore that upper limit. And then when we look at the lower limit, when t equals 0, then that's a 1. So that gives us a y at t equals 0 here. So that's from the first term that we get in this in this integration of products formula. And then looking at this function, we can see that we have what's in effect the Laplace transform of y itself here. So we can we can simply state that the Laplace transformation of y, we can label that as y dashed. And more naturally, we would use just a capital Y instead of y dashed, but we're saying dashed here because in this case, we were actually looking for the transformation of the derivative, not of y itself. So anyway, this is nothing but another Laplace transformation here. So it's in effect a recursive transformation. And so that's what's defined here. So our y dashed is defined in this way. And if it's the case that y at naught equals 0, and remember the deviation approach. So if we transform our equation lowercase y to the deviation version, then we typically achieve that it's equal to 0 at 0. So if this is 0, then we can say simply the transformation is equal to sy dashed. And that's quite a surprising result, I think, because it's telling us that if we take a derivative, if we take an operation like this, all we need to do is multiply s by the transformation of the function y itself. So that gives us a nice relationship. And this is why Laplace transformations are so powerful, that operations, calculus operations like differentiation can often be translated to almost algebraic operations only. So instead of ending up with a derivative, some kind of operator here, we end up with just s times. So we go into the space in Laplace transformations where the operations are much easier. They're quite algebraic to deal with. And so that's why we are able to do many things and find many more relationships in this alternate space. And here's just an example. If we apply this to our context of control. So in our control type problem, we have dy dt is some function of the state variable y itself, and there's some control action. In this case, it's just shown as a plus u. If we have a first order process, for instance, then this abstract function of y, that would be some constant times y, right? Again, for a first order process. And so if we Laplace transform this equation, then we would get s times y here. So according to what we've just set up here, the Laplace transform of a derivative is equal to S times the Laplace version of the equation of the variable itself. And then if we Laplace transform this, it's a constant times y. So this is ky. And then if we don't know what u of t is, then we'll simply state there's some Laplace transformation, and there'll be an s variable in u. So now we have an equation like this, and we can see y's on both sides. And so if we group out the y's, then we get the form like this. And then if we define the transfer function g equals y over u, then we can see y over u is going to give us the 1 over s minus k. So that's our transfer function for the first order process. And in fact, for higher order processes, let's say it's an nth order, we can show in a similar way that we get a standard form like this. Right, so that's what we get for derivatives. And we can also consider integrals. So if we are interested in the Laplace transformation of an integral in t, then we would apply the standard definition of transformation. So it's e to the minus st times the integral here, and all of that is integrated in t. So the inner integral goes from 0 to a current time t, and then the outer integration is integrating out over all times. And again, we can apply integration by parts and use f as e to the minus st and g as this. So if we do it that way, apologies, I see we've actually done it the other way around. So this is our f function, and this is the g function now. So we can see the f function, we know it's f times the integral of g. So the f we can see stays the same out here. And then the integral of g is going to be minus 1 over s e to the minus st, which we can see here. And of course, we are integrating 0 to infinity. So that's the first term done. And then in the second term, it's the integral of the derivative of f. So in this case, the derivative is going to give us f itself here, times the integral of g. So the integral here is going to be 1 over s e to the minus st. And I see we've taken the 1 over s out here, and the minuses have cancelled. And so we have this form. And now, again, we can see this is nothing but the Laplace transformation of the original y itself. So this term is looking like 1 over s times y, where y is the Laplace version of lowercase y. And if we look here, we can see at infinity, we've got e to the minus infinity, which is 0. So this whole thing is 0 at infinity. And then at 0, we've got the integral from 0 to 0. So this is a 0 area. This is the area under, well, there's no change in t here. So this is a 0 area. So this is basically a 0. So this whole term is a 0, leaving us with just this. And so that's what we have for the transformation of an integral. So we will use these Laplace transformations to help us investigate the plane of possibilities. So rather than working in the time domain, when we work in the S domain, we can find our relationships much more easily.